Our next speaker is Avinash Palaniswamy. He is the Chief Commercial Officer at Quantinuum, where he is responsible for sales, marketing, and delivering revenue, which is something I think both of the previous speakers would love to see coming from quantum technologies. He's played a similar role for Intel's high-performance computing and graphics group, as well as the data center and AI groups. He has multiple patents. He mentors various startups and has taken on leadership roles in the industry. So looking forward to your talk. Thanks for joining us.
Well, thank you. Appreciate it. Awesome. So, there's a little key here.
I'll give you a 5-minute warning, and that's your clicker.
All right. Perfect. Awesome. So hopefully today's chat is going to be a little bit about what I've learned, right? I initially had Reinventing HPC and AI. And then I said, well, AI is really an application in HPC, right? So I spent about 23 months of learning. And I know Worley is here. I don't want to be here for 8 more years and show the same slide and say 10 years of learning. Hopefully this is a fun chat, and I'll be flipping through some slides to keep within the time limit. But this is really about me as a HPC person coming into quantum and seeing all the types of issues that needs to be addressed to really move away from hype to reality and going to what our leader from DARPA said, right? Taking it to commercial reality. And I think you had a beautiful chart there, which I wish I had, that I can show here, but it is really one of those boxes, right, which is missing. I think that's the 5th box, which Worley should add to his slide on, what is needed to make quantum a reality, right? So just as an introduction, I came here 37 years ago, actually, and I'm here because of DARPA, so thank you. I did my research at University of Cincinnati and the Wright-Patterson Air Force Base, working on distributed computing. And what I'm going to tell you is pretty relevant to what, this journey is with quantum, right? Which is, when I graduated, I had a big 128 processor machine, a KSR, and 1,024 mass bars sitting in my desk at University of Cincinnati, thanks to DARPA, thanks to Dr. Hal Carter and Dr. Wilsey and several of the folks. But did it do any useful computation is the question. Okay, and when I graduated in '94, somebody read my paper, and it was Motorola, and they offered me a job. I moved to Chicago, and I used everything that I learned, right, on a very powerful machine. Okay, I actually graduated just because of a Sun 4-processor machine, okay, which could actually get real results in time, right? But all the work done on KSR and mass power was useful, right? And but it didn't bring that commercial reality, right? The stuff that really happened was that box you showed at the end, right, where you go from that big table into something that is usable from a software standpoint and a hardware standpoint, right? So we need to get there to become reality. But everything we're doing now is paving the path to that. Okay. With that, I'll get into some of the things. Before I go forward, I saw this today. Congratulations to the Texas team. New scientists put this out. Again, this is a step, forward to making progress, to making commercial things a reality. I also found out it was done on our machine. So, and I think Hunter is here. If Hunter is here, you should talk to him. It was only achievable on Quantinuum hardware. And I'm sorry if I bring in some of Quantinuum into some of those chats, but it is relevant to the progress being made in terms of quantum machines and where we need to do and what types of things that can be enabled. Okay. I know a lot of people are wondering what we are. We are probably the biggest quantum computing company on the planet. We have about 630 plus employees, 440 plus PhDs. I'm a PhD, but not a physics PhD. And I was terrible in the subject, so I enjoy listening to PhDs. And Dr. Mark, that was a fantastic presentation. Thank you. I learned a lot. We have about 670 plus global patent spending. But more importantly, we're trying to go and figure out how to make these things work. Okay. I'm not going to go into this. It's a little bit about our funding. But I think the key here is getting into what our leaders from DARPA said, what Worley said, is how do we make this deployable, right? And that's where we're building the expertise to go and do that. We have 3 generations of quantum computers already manufactured. We have 13 test beds in place, Okay? That's the only way you're going to go get to a commercial system. 13 test beds. And that is what we're checking every part of what makes a computer a reality. I'm learning this, 23 months of learning, okay? And we have two major fab partners, Infineon and Honeywell. We have 9 global sites delivering this commercial quantum computing, and we have about 5 commercial systems deployed. Okay? All right, I'll stop with our company and now go into some of the things I think which is needed to make this quantum computing a reality. Okay? I'm kind of like really tired, like whenever I wake up, right? I have like 20 results coming out, and fact of the matter is what Worley said, right? These are just paving the path. It's not bringing commercial reality. A lot of these things can be run on a laptop. Okay? So, but the future of computing, right, is really HPC plus AI plus quantum, CPUs plus GPUs plus potentially other accelerators and quantum. Okay? But what does building this winning future look like, right? When you're building a HPC system today, you know how to get a good system, right? You have spec FP, you have LinPack. If you want a memory bandwidth machine, you can use HPCG. You can have streams as another option. You have mini apps, which are there in application. When you see RFPs coming from the national labs, they have mini apps. If you see RFPs coming from several of the other labs, such as LRZ in Germany, for example, they'll put 40 real applications. Okay? You have to have the capability to project and actually go and deploy these systems. And you get a penalty if you don't reach those benchmarks. So on the HPC side, you have real benchmarks. That goes into what a DARPA leader showed in terms of a benchmark boxes, right? In quantum, it's lacking. Okay, that's my key thing over here. And AI, there's ML perf, there's AI flops now, right, which represents the system. And you can see who the clear leader is in AI. You can see who the clear leaders in HPC. Quantum is a big question mark. So that comes into this question. I usually have this as what makes a good quantum computer. And I figured there's a lot of the HPC crowd here, so I said, what makes a top quantum 500 computer, right? So many things. This is the 23 months of learning. What I learned was that for a quantum computer to be useful, okay, it has to be universal. Basically, it's got to support 2 types of gate sets. It also has to be fully fault tolerant. Okay, 10 minus 3 is great. We have 3 nines physical fidelity. With the logical, we get better. Okay, but you have to make that progress into something which is like your laptop. Okay, that's what is going to bring real quantum computing. Okay, I always hear about like fault tolerant algorithms. Great. Okay. In order, right, to have a real quantum computer, you need to support a universal gate set, both Clifford and non-Clifford, and all the operations need to be error corrected, just not a few. Okay, that makes it fault tolerant. I was like, whoa. There's a lot of things that need to be done to really have a true quantum computer. It's got to be universal, gate set, it's got to be fully fault tolerant. All right, okay. So when we started last year, we went in front of, I think it was in Quantum World Congress, really, right, if I remember right. We went and said, you know what, we're not fully there, okay? We really need to go and get the non-Clifford gate set. If you just have a Clifford gate set, you can simulate the computer, on any HPC computer. You need to go do non-Clifford gate sets, right? And oh, by the way, if you want a real computer, okay, and you want to use it in real practice, you need to have it with repeated error correction, okay? And that is what we went about doing for 1 year, right? How do you get to a true, universal, fully fault-tolerant quantum computer? We have shown that with industry first. It's a 2-qubit non-Clifford gate on a commercial quantum computer at 10x better, right, than break-even. Meaning, when you take the physical one and the logical one, we're 10 times better. Is that still ready for using real applications? No. Okay? But it's a path forward. Okay, we're the only ones who've shown that. And we need to get there, right? These are the little steps that we need to do and the benchmarks we need to do, right? These are some world records we did just to get there at this moment. We hope it's broken by the community so that we can actually get to real quantum computing, okay? I didn't even know what a magic state was. I was like, whoa, what are magic states? How many of you understand magic states here? Fantastic. You know what, I'm going to talk to you and understand it better too, right? So, in terms of world records for universality and logical qubits, right? These are some of the things we did, okay? But ultimately, if you look at HPC systems, you have something as simple as LinPack. Okay, you know what? Run LinPack, it actually represents something in the system. You run HPCG, you can have a great memory bandwidth system. So, one of the things we have adopted was IBM's benchmark. We said, hey, if we create a benchmark, people are going to be like, hey, you did it just for yourself, right? So we use quantum volume, which is, I believe, at this moment, the closest to representing, the value of a quantum system. So we have gone from 8 million to 33.5 million, okay, as of yesterday, right? We published it yesterday. Now, the second company is at 2048. Okay? Does this mean that we are going to go deploy a system? No, but we are making that path forward. We're making giant leaps, okay, towards executing on a roadmap. Okay? So that goes back to, the benchmark part of it. That we really need to establish benchmarks, right, that are representative of quantum systems and that everybody can publish. Okay, everybody publishes something, and so nobody's got an idea of what is, really a great, I used to call it a good, quantum computer. Okay. So it's a International Year of Quantum, so we are celebrating as a company, right, with 8 world records, and we hope to do it every year on a path to a roadmap that I'll show later. Okay, this was purely synthetic, right? We need to talk about applications. How does a quantum computer do with applications? We do something, people are not going to believe it, right? So we look at third parties. This is an example, okay? Somebody sent this to me. This is done by a third party, by Ulick and Purdue. And this showed an example of, a computer with more qubits than us, but at about 20 qubits, it becomes noise, okay? So we need to do more of this application level kind of benchmarks, right? Spec FP is a great number for a CPU, spec FP rate. Okay, we need to come up with a benchmark, right, which can actually represent how an application does, which everybody accepts, right? So this is something that I would ask, the whole industry to get together, right, and make it impartial about modalities. From my standpoint, I don't care about modalities. Let's be very clear, right? It's really about getting to the applications and the benefit. Oh, don't forget the software stack. Okay? This is key, right? One of the things we have done at Quantinuum is we want to make sure we have a standard open source software stack. You may have heard about Ticket. We have open sourced it. We have, we worked with the industry to create an intermediate format called QIR, right? It's open. And we have worked with we just created something called Quantinuum Guppy, which is really a program which makes it much easier, more C and C++ like, to write your quantum programs. Okay? And that is open also. The key to making quantum computing successful is going to be how open we are and how interoperable software is going to be on multiple platforms. Okay? All right? Now let me come to the original part of my talk. So what are we reinventing in HPC? Right? I think today if you look at the 3 big things happening in the world, one is, of course, HPC is, I know a lot of quantum people will walk up and say, you know what, yeah, those HPC computers are terrible. They don't do anything, right? You need quantum computers to solve stuff. It's not the truth. You're driving cars safely. You're driving self-driving cars safely. You have airbags. You're on planes, which are beautifully built. So HPC is probably the most valuable tool today with CPUs and GPUs, providing you safety, right? It's providing you a better quality of life. Generative AI, right, is something that is, I think, revolutionary. I think what Jensen and his team have done is just tremendous. Okay, and quantum has the potential to enhance and extend AI. Okay, this is kind of what a vision that we have, where we have classical data and quantum data. The quantum computer is used to generate data, which is used to make your large language models better, in a nutshell. So you have a better AI science assistant, and we're working on several use cases in quantum chemistry, materials, and data analysis. Now you ask, hey, when is this going to be real, right? We believe data analysis will be real with our machines in 2029. We call that machine Apollo, okay? And hybrid is more than just AI. This is an example of what we have done with Fugaku in Japan. This is not solving, all this is showing is that using a hybrid platform, you can get close to classical, right? This is not saying, I don't like the words quantum advantage or quantum supremacy, right? This is really showing that there is potential here, okay? Okay. And one of the things from a company standpoint is we are focusing on execution. We believe this is the age of acceleration. And when we get to Apollo in 2029, there's a reason for that. We believe we are in the age of scale. But it's not going to solve every quantum problem, okay? But it'll solve certain types of problems in combination with CPUs and GPUs. This year, we're going to have a new machine called Helios. It will be the first 50 logical qubit commercial system. This is our International Year of Quantum present to the audience here. Okay. And this is a year of breakthroughs. It's been a hectic year. 23 months, I've lost more hair than you can ever think. But, finally, I think we can get from Apollo in 2029 to 1 million plus qubits, right? We see a path, in a company to do that. And we're excited about it. We'll talk more about how we get there in future, discussions. My CEO loves to say this, and I believe this too. I'm 58 years old, and the pace of change has never been this fast. Yet it'll never be this slow again. And I'm looking to the new generation, of folks sitting here to make this a reality. And thank you. Appreciate it. Yeah.
Questions? In the back, can you find a microphone? You may have to walk up closer here.
By the way, as you're finding, I've been living in Texas since 1997, and I'm probably more Texan than most of the folks here. And I love Texas, and thank you for coming for Texas. And we will have the biggest quantum computer here, just like we have the biggest HPC computer for NSF here.
Microphones are right back there.
All right, Emperor's New Clothes. Okay. So why does everybody want to work against nature to correct the error? Why can't we have the uncertainty? Why can't we have the error to help perturb the data and, make the art and make the AI training more accurate?
I think that's a very good question. In fact, I was speaking to Hunter today, and he was actually giving examples of where having noise makes the applications better. But I'm not the right person to answer that question. Okay, in terms of why we can't have a noisy system or a noiseless system. Of course, 2 years ago, before I joined Quantinuum, we showed that you can actually simulate a topological qubit on a machine, right? Is topological qubits the answer, right? Where we have actually nature's quantum error correction? It remains to be seen, okay? And I think, can our computer use a topological qubit approach instead of using quantum error correction? I think the jury is still up on that. Yep, but I think there is a possibility. You can use those topological qubit ways to actually have, theoretically, better than quantum error correction approach to systems.
So
All right,
you.
with that, let's thank Nash
Okay.
again.
Thank you.